Okay. So fine. So let me recall us briefly what we have proved and what is required to complete the proof of the theorem. And at the same time tell you that what is the part which I am going to cover and what is the part which I will not be able to cover. All right, so we have proved the following theorem, decomposition theorem in an abstract setting. That such that the following holds. For any function f z mod pz to r plus, satisfying that you have there exists a function nu this cut norm is small. I can write, we had proved the general norm such that the dual of it is an algebra norm, but now we know that our cut norm is satisfies those properties. So therefore, I can write down this. Is at the most 1. Then f is equal to f belongs to all right. That is what we have proved so far. And then another thing which we have proved is that if you take, so P1 is a subset of primes intersection 1 to n. And you take W is equal to product P less than equal to log n by 2, let's say, P. Then there exists B Z mod WZ star such that I'll assume that cardinality P1 is greater than equal to alpha n by log n. Alpha is a fixed number, positive number. Okay. This is greater than equal to or greater than maybe greater than equal to alpha by 2 log n by log n by W. Yeah. So let me call this set as a P1B. So this P1B is it can be also written as a those n less than equal to n by w such that B plus Wn belongs to P1. Okay. Okay. Sorry. This P1B minus B by W. I translate it and divide by W. Then this is basically those n's such that B plus Wn is prime. Belongs to P1. Now P1B contains an arithmetic progression if P1 this particular set contains a arithmetic progression because it is just a translation and dilation of the P1B. Okay, and if this particular set contains an k-term arithmetic progression, then this set contains an arithmetic progression, and this set, if this set contains an arithmetic progression, this being a subset of P1, the set P1 contains an arithmetic progression. Okay, so let me call this set as a P1 prime or whatever. For some reason I use the notation this A B zeros. Let me just be consistent with that. Okay. Because I was doing for the general things, working with the general thing. Let me be consistent with the notation which I am being somewhat comfortable. Okay. So now, okay, so the AB0 is a subset of 1 to n by W. Then we choose prime P greater than equal to k and W, kn by W, and less than equal to 2k n by W. And write the function from z mod pz to r plus to be f is equal to the AB bar by cardinal TAB bar. Okay. And we would like to apply cardinality AB bar. No. Not cardinality, density of it. So this is prime is of the same order as n by W. So I will divide by basically log n by alpha log log. Okay, so that the average is around 1. Okay. Now this particular function, as we see that this is not bounded because it is this log n by log log n, and that is tending to infinity as n tends to infinity. So we would like to apply decomposition theorem to this particular function. So the theorem which we need is the following. Which we shall prove is that there exist for P sufficiently large depending only upon k and alpha, okay, there exists V from Z mod Pz to R, I mean the P will be this particular P, all right, such that O of log P cube by log P. Okay? You may ask, and rightly so, that I mean I am taking the fix this function V is actually a function from a fixed Z mod Pz to R, and why am I writing this O of these things? Because basically this will be a sequence of functions. For every prime P, as n increases, the P increases. So you have a sequence of this AB, and for corresponding to every this AB, you are associating this F. For this every F, you will get this V, such that this norm V minus 1 will be O of log P to the cube by log P. All right? So, fine. So, once we have that, then since this is log P to the cube by log P, that is tending to 0 as P tends to infinity. And therefore, the conditions of this particular result will be this particular theorem will be satisfied. Because for large enough P, this will be less than equal to epsilon, whatever the epsilon I want. All right. So in order to prove this particular result, we will actually not prove this for the cut norm. What we will prove in fact is that the norm of V minus 1, some certain Gowers norm is small. All right. Then we will need a lemma which says that the cut norm is less than equal to Gowers norm. So therefore, if I manage to show a function nu such that which dominates this particular function and which satisfies this property that norm V minus 1 Gowers norm is small, then I am happy. But this is something which we will not, though the proof is not too complicated, but we will not prove it. Proof Conlon-Fox-Zhao Green-TAO theorem exposition. So anyway, if you type in Google this words, even if I have slightly done here and there in the title, you will find it. So yeah, Google helps a lot in searching. All right. So okay. So this is what we will but still, of course, this does not prove the result. Although we are in a position to apply this particular theorem, but what to do with this theorem? We can't do anything with this theorem unless we know that if f is equal to f1 plus f2, once we have this theorem, we know that a gamma k f1 is large, but unless I know that a gamma k f2, this f2, since its cut norm is small, that fact implies that this number of k-term arithmetic progressions in corresponding to f1 and f are same almost. Unless I have that counting lemma, it is of no use for me. So I will indicate here again, I will not prove this particular result, this counting lemma. What I will indicate is that if I would have had a stronger assumption, namely the Gowers norm of f2 is small, this particular theorem is not telling us that a Gowers norm is small, because the Gowers norm is bigger than the cut norm. This particular theorem is telling us that the cut norm of f2 is small. But the Gowers norm is a bigger quantity, so therefore that can be very large quantity. So in order, if I want to apply this particular result, then I have to show that the counting lemma with this particular norm. But again, I will not prove, and I will again refer you to Conlon-Fox-Zhao thing. So only thing. But of course, once we have this counting lemma and this particular result and this particular thing, then we have our theorem. This particular lemma is not very long, whereas the counting lemma in case of Conlon-Fox-Zhao is not as simple as in the case of the Gowers norm business. It is not very long, but you require some ideas there. Which are actually pretty important ideas, what they call densification. And which has helped in obtaining the polynomial patterns in primes. In the work of TAO and Ziegler, they used the idea involved in Conlon-Fox and Zhao for their work in polynomial pattern in primes. On the other hand, the Gowers thing is, although conceptually not very so difficult, but the one difficulty with these things is that it can be notationally intimidating when you see it for the first time. Okay, so if you can overcome that, then one can follow. All right, so I want to prove this particular result. Which will not complete the proof of the theorem, but that's all what I will do. So in order, okay, so in order for me to explain the how we are going to prove this is result, I need some definitions and notations. Be an affine linear map. Okay, what do I mean by affine linear map? It is just a translation of a linear map. So that is for some C belongs to Z to the R and phi linear. Okay. So what that means what? That the phi is equal to phi 1, phi R from where phi I of x1 xq is equal to summation aij, j is, how do you write a1 what? J is equal to 1 to q x. Okay. That is what it means. So we will say that phi bar is of finite complexity if for all I not equal to j, phi I is not equal to C phi j for some C belongs to Q. Okay. So let me give an examples. Okay. This phi I, once you have this linear map, it will also introduce a map from, it will induce a natural map from Q to, from the rationals to the power Q to rationals to the power R. And we are saying that none of this phi I and phi j are linearly dependent. No phi I is linearly dependent on another phi j. So for an instance, phi from z square to z to the k, phi of x comma d going to x, x plus d, x plus 2d Okay? This is of finite complexity. Because if you take any two of them, x plus d or x plus 2d, you cannot, any two of them, you cannot write one in terms of the other. Okay? Here what is the phi1 xd is equal to x, phi2 xd is equal to x plus d, and phi k xd is equal to x plus k minus 1 d. This is a fine, so take any two of them, they are not dependent on each other. To see this, I mean, for instance, if you want to see x plus d and x plus 2d are not linearly independent, x plus d is equal to 0 does not imply x plus 2d is equal to 0. If they would have been linearly dependent, then one is 0 implies the other is 0. So this is finite complexity, not, so if I am giving finite complexity, I should give which is not of finite complexity. So if I take phi from z to z square for an instance, phi of x goes to x and x plus 2. This is not a finite complexity. Because here what will be the phi1 of x is equal to x, and phi2 of x is also equal to x. Because in order to do this, I have to only worry about the linear part. This is the linear part. So this is equal to xx plus 0, 2. Okay? So the linear part of both them are same. So this is not a finite complexity. All right. So fine. We shall define the norm of sum of all the modulus of the coefficients involved in the linear part. All right. Now same way I can define from the z mod pz also. All right. The same way I can define for the z mod pz, the same definition. But what will be the only thing now I have to do, okay? I have to yet to define the norm phi bar p. Okay. But before that, let me just write down the lemma, which I will just let be an affine linear map of finite complexity and P is larger than P is sufficiently large depending upon this phi, P is a prime sufficiently large depending upon this phi, then it will also induce, then phi bar induces a map from Z mod Pz to the Q okay. It's a thing with the integer coefficient, so it will respect the congruences. So it will induce a map from the Z mod Pz to the Q to Z mod Pz to the R, and it will be, but it may in general be not be of the finite complexity, because if the if I take x and 2x, okay, x and x plus 2y, suppose I take phi x y is equal to x and x plus 2y. Then in Z, this is of finite complexity, but mod 2 it is not finite complexity. Because when I am reading mod 2, it will becomes x and x. Okay? But if P is different from 2, then it will be of finite complexity. So therefore, if P is sufficiently large, then this will induce this map, which will be of finite complexity. So again, then the induced map is of finite complexity. All right. So I have to define what is given. So for any x belongs to Z mod Pz, okay, y bar means the image of y in Z mod Pz. So there, say if I am taking this is okay minus p by 2 to p by 2, choose a unique integer. So that is how I am defining this mod x to the p for any x belongs to Z mod Pz. So now if I have been given phi bar phi f from Z mod Pz to the R, and I mean phi bar, okay, phi bar is equal to phi plus some c. C is some number in Z mod Pz, and actually phi is equal to phi 1 phi r. Okay. So yeah, now I can just define here the phi I is equal to this, just all right. So now support of a linear form Ez is a linear map with phi I of xq, then support of phi I is equal to those j's such that aji not equal to j. All right. Now phi is equal to, suppose phi is this affine linear map, and phi is equal to phi plus c with q linear map. We say phi is in S normal form at I if there exists a subset gamma I contained in support of phi I, okay, with the cardinality of gamma I is less than equal to S plus 1. I will, so this definition may look a priori somewhat funny, but I will, this is what I was trying yesterday to reparameterize things in a manner so that I can get rid of the other functions. So I will explain it. So if there exists gamma I contained in support of phi I with gamma, the support is these things, such that gamma I is not contained in support of phi j for j not equal to I. Means that if you take phi j different from I, then there exists at least one element from the gamma I which is not there in the support of phi j. All right? Now using this, let me prove this configuration control lemma for the bounded functions at the moment. What is this control lemma? So okay, so before controlling the before proving this control lemma, let me let me now define this definition of Gowers norm, which I have postponed it for too long. You don't need to assume that the functions are real valued, but I am just defining for, it is not particularly more complicated, but just like. Too small? Right. So let me illustrate. So I will not prove that this is a Gowers norm. Means this is a norm. In order to prove this, I have to show that this first of all is a norm. I will not prove it. Yeah. So in particular, for an instance, okay, this corresponds to W is equal to 0 everywhere. This corresponds to W is equal to 1 comma 0. This corresponds to W is equal to 0 comma 1. This corresponds to W is equal to 1 comma 1. Similarly, norm f 8 u3 h1 all right. Of course, I have not even shown to you that the right hand side is positive, so that I can take its so that the norm is a positive quantity. But okay, I'll leave it. But indeed, it is a norm. It satisfies. So now this, oh boy, I did not remove that. This S normal form. So first of all, let me state a result again, which neither I explained to you precisely, nor I will, and since I am not going to state it precisely, I am not going to prove it either. That if a linear form is of a finite complexity, then it can be. Okay, so phi is in S normal for M at I if these conditions are satisfied, and phi is said to be S normal if these conditions are satisfied at every I. Okay, so the theorem here let F1 Fk from Z mod Pz to R to, let's say, -1 to 1 be functions. Let phi bar phi1 phi2 Z mod Pz to the Q Z mod Pz to the R be an affine linear map which is S normal then minimum over I yeah. All right. So okay, let me prove it when S is equal to, let's say, 1. And suppose phi1 of, suppose tau 1, which was the support, so that it depends, the phi1 should depend upon the tau 1, the elements. So therefore, there is a cardinality of 2 things. So okay, so I will just let me assume that phi1 of x1, x2, x3 is equal to x1 plus x2 plus x3. Now I am cooking up these things which I have not cooked up before. Just tell me if this avoids, so I don't want this thing to depend upon x1, so I will write x2 plus x3. All right. So now in this case, for this particular, so now I am taking this phi to be equal to, or maybe I write down 2x1 plus 3x2 plus x3 because that will be slightly important. I will get rid of this 2 and 3. Finally, we will be able to get rid of 2 and 3. Or here, 5x2 plus 6x3, 7x1 plus 8x2. Is sufficiently large, take it bigger than all these numbers. And so, okay, so I have been these things and I want to prove F1, F2, F3, and I want to prove that what is norm F1, U2. So let me explain the proof in this particular case, which will, and the proof for the general case is not particularly more complicated. It is only that the notation wise it is more complicated. All the ideas which are required to prove the theorem are already there in this particular case. So I have to obtain a bound for x belongs to x1, x2, x3 belongs to z mod pz to q z mod pz, and you have a what? Can you read it for me? F1 of what is phi1 of x2? 2x1 plus 2 plus x3. F2 of 5x2 plus 6x3, and F3 is plus 8x2. All right. So now this F2 does not depend upon x1. So as we did yesterday, what I will write? x2, x3. So of course the f1 will remain inside. So according to the elements of this gamma 1, I will keep on applying that take the element of one particular gamma 1 inside, and let the elements which do not depend upon this, let them remain outside. So which are the elements which do not depend upon? So f2 does not depend upon this. Okay. So when you apply, this will be less than equal to E x2, x3, and apply this particular thing to the square. This will be less than equal to x. Right? Now f2 has gotten rid of. And what has happened? That x1 has duplicated. Because I have applied the Cauchy-Schwarz, the variable x1 has become the x1 prime as well. Similarly, I will apply again, take the x2 to be inside. When I take x2, or what was it? So what was, maybe x3 to be inside, then this f2 will come out, and then that would have also gotten rid of. And again the x3 would have become one more. So in this case gamma 1 is what? Gamma 1 is x. What is gamma 1 here? x1, x2 or x? Okay, x1 has duplicated here because I took out this one outside. Then the next time I will take to be x3. So x1 and x3 will duplicate. So since I am going to apply again Cauchy-Schwarz, so therefore this will become 4. And what will happen now? E x2, x3, x1, x3 prime, x1 prime belongs to Z mod pz. Because of the duplication, whenever I apply Cauchy-Schwarz on the inner one becomes the duplicated, the variable, and this will become what? x2 is not duplicated, all the other variables are duplicated, 2x1 plus 3x2 plus x3. All the functions I have gotten rid of. f2 of to x1 prime plus 3x2 plus x3, f2 of 2x1 plus 3x2 prime, x3 prime plus, x3 prime plus x2, f2 of x1, x1, now 2x1 prime plus 3x2 plus x3 prime. That is what it will become. Okay? So now first of all, I just get rid of, since as x1 varies over the Z mod pz, 2x1 also varies over the Z mod pz. And there is nowhere 5x1 is coming. So I can erase this. As x1 prime varies over all the Z mod pz, 2x1 prime varies over all the Z mod periods, so I can erase this also. In fact, I can erase all these coefficients. Because now there is only one linear form to worry about. Okay? Another thing is that this, I mean, everywhere it is plus x2, same x2, because x2 has not these things. So for now the okay, I'll do in 2. Now I will make the change of variable x1 prime is equal to x1 plus h1. Okay. Similarly, x3 prime is equal to x1 plus h2. As should have been okay. Okay, whatever. This should have been better if it was a h2. But okay. So now so here it will be x1 plus h1. Okay. Now I make another change of variables by saying that x1 plus x2 plus x3 is equal to z. And once I do that, I notice that this is exactly the Gowers U2 norm. All the other variables will simply disappear because there are more variables here than is there in the Gowers norm, but they disappear. All right, so in the afternoon, I will try to complete the proof, or at least indicate to you the proof of that it is. I have not even stated the result which I